Ini salah satunya. ಹಲೋ. ಹಾಂ, ಹೇಳಿ ಮ್ಯಾಮ್. ಹಾಂ, ಕೇಳಿಸ್ತಿದೆ, ಹೇಳಿ ಮ್ಯಾಮ್. ಓಕೆ, ನೀವು ರಿಸೋರ್ಸ್ ಪರ್ಸನ್ ಜಾಯ್ನ್ ಆಗ್ತಿದ್ದಾರಾ? ಹಾಂ, ಏನು ಹೇಳಿ? ಹಲೋ. ಹಾಂ, ಓಕೆ ಓಕೆ. ಹಾಂ, ಓಕೆ, ಇನ್ನೂ ಜಾಯ್ನ್ ಆಗಿಲ್ಲ. 5:30 ಆಯಿತು. ಓಕೆ ಓಕೆ.
ಹಲೋ.
57, ಓಕೆ, 57 ಇದ್ದಾರೆ. ಹಾಂ, ಓಕೆ ಮ್ಯಾಮ್.
Hello, Dr. Daniel. Hello, am I audible? Dr. Daniela, ma'am, can we start?
Yes.
So, good evening to Dr. Daniela Lopez Dulus, our guest and speaker for today's international webinar. And good evening to all the participants. On behalf of Dr. Ambedkar Institute of Technology, I, Dr. Nandini Prasad KS, Dean Foreign Affairs, take immense pleasure to welcome all for the international webinar on natural language processing as a tool for reasoning. I request our beloved principal, Madam Dr. Meenakshi M, to deliver welcome address. Over to you, Meenakshi ma'am.
Yeah, thank you. Good afternoon to all. I welcome all of you for today's webinar on natural language processing and the tools for reasoning, organized by the Dean Foreign Affairs, Dr. Nandini Prasad. And I welcome all the participants for today's webinar, and also I welcome the speaker for accepting our invitation and spending the time with us today. I welcome you, madam. And just to introduce about our institution, the Dr. Ambedkar Institute of Technology is established in the year 1980. In the beginning, we had 3 undergraduate programs, that is core engineering programs, electrical engineering, mechanical engineering, as well as civil engineering. And finally, 8 more UG programs are added and 10 PG programs are also added, along with the research programs in all the discipline. Our institution is 41 years old institution, accredited by NAAC with A grade, and also it is all the eligible programs are accredited by National Board of Accreditation. Our institution is recognized by UGC with the 12F certification as well as 12B certification, and we have the rankings, NIRF rankings, and recognized by in the national global level. And today we organized a webinar on natural language processing, which is broadly defined as the automatic manipulation of natural language like speech and text by software. Computational linguistics is the study of computer systems for understanding and generating the natural language. Here, new and different things can be discovered from large data sets of text by writing and running software. Statistical machine learning began to replace the classical rule-based approaches to language, primarily because of their better results, speed, and robustness. The statistical approach to studying natural language now dominates the field. Computational linguistics also became known by the name of natural language process, or NLP, to reflect the more engineer-based or empirical approach of the statistical methods. Computational linguistics has a scientific and an engineering side. The engineering side of computational linguistics, often called natural language processing, is largely concerned with building computational tools that do useful things with language. Example, machine translation, summarization, question answering, etc. Like any engineering discipline, natural language processing draws on a variety of different scientific disciplines. The webinar today but we organized with the title Natural Language Processing as a Tool for Reasoning mostly brings in more updates on the topic that is the need of the hour. My best wishes to the organizers and regards to the speaker for putting efforts in conveying the importance of the topic. With this, I welcome you, Madam, again. I request you to take over.
Thank you, ma'am. I now call for Mrs. Yashaswini, Coordinator, International Admissions, to introduce about our speaker. Over to you, Yashaswini.
Thank you, ma'am. Good evening, one and all present here. It's my immense pleasure to introduce Dr. Lopez de Luis Maria Daniela, Director, Computational Intelligence and Information Systems Lab, Argentina, Director, Intelligent Technologies Research Lab, Argentina. She completed her graduation degree in System Analysis, Engineering degree in Computer Science, degree in Expert System Engineering from various reputed universities. She obtained her doctoral degree from National University at La Plata during 2008. Maria Daniela's current research interests on natural language processing, machine learning, and intelligent reasoning, chatterbots, and autonomous mobile robots. Morphosyntactic linguistic wavelets, automatic reasoning, harmonic systems, and time mining. She has created few theories on emerging areas like morphosyntactic linguistic wavelets, automatic semantic by a wavelet-wise decomposition, harmonic systems, a lightweight time prediction approach, bacteria consciousness, creativity of consciousness in applied robotics, currently working on chaos and language theory to produce and process natural language. She has many fellowships and awards to her credit. To name some, member of the Scientific Society, Argentina, outreach project leader for science, technology, engineering, and mathematics activities, associated editor of IEEE, Latin America Transaction, Advisor Committee, Swiss Innovation Valley, Director of Computational Intelligence and Information System Lab, founder of local branch and leading member of IEEE CIS Game Technical Committee. And she was also a professor in National University of Technology, and also she served as a teacher in various reputed universities, and also director of Project Learnitron and CAEITI Research Center, and also the consultant in intelligent systems, soft computing, member of Women in Computational Intelligence, Argentina, member of Women in Engineering, Argentina, member of IEEE Site, Argentina, founder of Argentina chapter of IEEE Computational Intelligence Society, and current vice president, consultant in AI for gamification and STEAM, sentiment analysis expert, design and development of sentiment analysis, and she has received awards, the prize from IEEE Foundation Funds of Project MIDA during 2014, IEEE Computational Intelligence Society recognition for notable services in 2011 to 2012, and the list doesn't end here. I feel privileged to introduce Maria Lopez for the session. Now I would like to hand over the session to you, madam. We look forward to hearing your presentation. Thank you.
Thank you for your invitation. I hope you can listen to me okay?
Yes, you're audible.
Okay, I will share my screen. Okay, today I will speak about natural language processing and how we can use natural language as a tool for reasoning. Language distinguishes humans from the rest of the species. In fact, it is so important, so relevant, that during childhood it allows to a proper cognition evolution and for emotional and social maturity. So patients like autistic child can't develop a proper language, so they can't communicate with the rest of the world. They have severe problems with the socialization and with the proper emotional maturity. Language has many very specific characteristics that scientists in the field have been find out. For instance, language follows certain very precise rules, which we name as grammar. We will speak about that later on. But natural language is a system, a complete system, working under several and precise laws. Some of them have been found to be like the chaos theory. But there are several productions of the human brain that show us that it works like any other productions of the nature that follows apparently a logarithmic behavior and even certain fractal behaviors. As we will see later, our brain works again with these precise mathematics laws or rules like logarithm, natural logarithm, and certain fractals. There's an inborn strategy that underlies the brain mechanism. And we speak and we write text following these inborn strategies. Even when we perform mathematics, we are trying, and specifically when we are very, very young, where we use these inborn strategies. One of the scientists that I will mention later is Zipf, a mathematician that has discovered, for example, that when you choose certain words to perform a text, for instance, you are writing a book, a tale, a novel, you are choosing your words following a very specific distribution. This distribution is something like known in the field like Zipfian law or Zipf law. That later on it was adjusted by another mathematician named Benoit van der Borel. From the resulting of this discovering, there was several papers that follows this frame, this concept, and developed several other theories and testings that shows that language is not something ad hoc, but laws, the laws of chaos, and also certain fractal behavior. The curve that you could see here is the Zipf, original Zipf, not the Zipf-Mandelbrot, but the original Zipf distribution. Here you can see from a real text. I can't remember if it was a Quixote or something. It was a bestseller textbook, but you can see here how every word, this is on the x-axis, there are the sequence or the order of the word, and here's the frequency or the probability. You know, these are similar numbers. You can see that the distribution of the sequence against the probability of finding certain word follows this asymptotic curve. And Zipf was the first scientist to discover this law. And it indicates that we are not using an ad hoc word. We have certain inborn strategy to choose words. If you try this distribution in other books, in any language, you can find it. There are minimal differences, but you will find a similar curve for any text of signals that by convention you assign some meaning and you relate it other in a specific way. So what is different in the natural language? Well, human language, natural language, is a unite with the highest productivity. It's a perfect generation system for sentences. So with we will see later that with a few rules and with a very specific lexicon, you can produce several hundred or even thousands of sentences, and you can provide a communication bias, very, very practical and very performant. So let's understand how the language works. The first of all, we have to understand that communication is inside every sentence and every language production. So when we produce something, a piece of text or a speech or a symbol to even to communicate something, there's an information to be transferred from some sender to a receiver. This is a very classical point of view in recent findings, recent researching. There's something that has been changing. It's not so linear, but in order to find out how the communication process works, mainly it is okay for now. So there are several steps in the sender and in the receiver in order to produce a successful communication. The first step is that sender has to determine when and what information wants to communicate. This is called strategic generation, also called the aim step of the communication. But after you decide when and what information wants to communicate or transfer, you have to encode, to perform translation from what you want to say, what you want to inform, and the specific encoding. So you have to determine a set of rules and lexicon that will be understood by the receiver afterwards. So the generation is a very critical step in this workflow. The third step from the sender is to synthesize the information into a message. This is you can say it like a practical step, the first evidence of your communication. So you have to synthesize, that is, you have to write the text, you have to produce a sound, or to draw a signal. This is the synthesis. Afterward, you have to send this message to the receiver. The big arrow in the middle is representing this passage, this transferring step that is not in the sender, is not in the receiver, but through a channel. The channel could be the air if you are speaking, a piece of paper if you are writing, or something else. When the channel ends, you will find a receiver. The receiver is the one that has to decode, to understand the communication and to drift off your message. Then the first step is the opposite of the synthesis. That is the perception. You have to receive the sound, you have to read the text, you have to watch a symbol, and this is the reception. Afterward, you have to decode using the same grammar, the same decoding steps. Usually, this grammar is involved with some syntax, some semantics, and a pragmatics level. All of these we will see later. But the decoding step just is half of the problem because the receiver has to validate the information. You know, if you don't understand the decoded message, if you can't decode it properly, you can't validate and you can't understand what the message is. So it is a very important step that is usually not considered as relevant, but it is relevant because if I use something that is not in a syntax or in the semantics or cannot be inserted in certain pragmatics, you can validate it and you will not be successfully in the reception. So the validation step is the one that can determine if you can insert in certain part of your knowledge structure. You know, every person has a past, has a set of information, knowledge, and has also a structure that is a consequence of the past and the learning and the studies, etc. So after validation, you have to insert this knowledge, even if it is a false knowledge or a false or a true validation. No matter the result of the validation, you always have to perform this step. But if you can't perform the validation, you will never insert the knowledge and it will pass through as in any other thing. This is a graphical explanation of communication, but from the linguistic perspective. Imagine that you are speaking and the system, you have a system that has to automatically process the receiver steps. So you will start with a sound, you speak to the system, and this sound will be received by the system with something, a microphone, it doesn't matter now, but the linguistics starts when phonetics processing is performing. So the process is not complete just with phonetics. Phonetics means to gather every sound pitch and to transform it into a letter, into a word, or a signal. So you have the phonetic step always problems with related with disambiguation of sounds or finding certain noise, and you have to clean up the sound or parse the sounds. You know, when you think a word is ended, it's not an easy task to detect the silence and to detect when a word starts and when a word has finished. It is not so easy in an automatic system. So after phonetics, you will get a word or a set of words, but they have no sense. They are just words, a bag of words, and you have to start the syntax step. Syntax is related the study of how words relate each other. So when you perform syntax, you have a predetermined syntax structure, and the only activity here is to match which structure is good for this set of words, for this current sequence of words. So syntax just detects as a pattern matching function which syntax structures are currently in your communication. So the outcome from syntax step is a set of syntax structures detected. In this step, you can find several approaches and tools like Noam Chomsky's trees, that is a type of trees that detects the syntax structure and the types of words that you have in your communication. And you can also have other syntax structures like the parsed structures in morphosyntactic linguistic wavelets. The important thing here is that you have not a meaning. You don't understand yet what is in this text or in this communication. You are just preparing the encoded message just to start processing what the meaning is. The next step is the semantics. I can tell you that semantics is the most difficult step that is up to now the focus of the scientists in this field. Semantics seems to be easy, but it's not that way. Semantics is related to looking for understanding what's the meaning of certain sentences. But the meaning is literal. That is, you know, when you use, for instance, Google Translator, it uses this type of semantics. You can see that the translation is okay, but word by word, and if you don't understand the whole paragraph, it performs certain mistakes because the meaning is literal. But sometimes, you know, you have to change the semantics in order to adequate the semantics to the whole text or the context of the communication. But this step is not does not deal with that level of semantics. So the next step is the pragmatics. Is when you understand as a native in certain language, you understand that, okay, yes, the sentence is okay, but not fully okay. There's something wrong here that not fits exactly. This pragmatic level, I can tell you, is not covered up to date in any work in the scientific world. This is very, very difficult to insert pragmatics because you need contextual information, information that is not usually in the text or even in your neighborhood. You need probably cultural clues to denote why certain word is used that way. Certain pragmatics could be gathered, for instance, if you process in the context of reduced domain communication. For instance, when you are using a slang, if you are communicating in electronics, you know certain words will have priority means, and others will not. If you are working in the academic field, you will use certain words more than others. So this is pragmatics, and it can be enclosed in certain universe, but this universe is not so small and not easily gathered. So sometimes we have a message that could belong to many universes. For instance, if you are speaking to a friend, you are speaking with a slang, you are speaking because you are young with certain words, or you are speaking because you are in a country, or you are in a time of the day. So pragmatics is very, very hard to overcome. You have to survive to these types of challenge, and it is not an easy task. Up to date, linguistics has not solved this problem. Even semantics is a current challenge. So to make you, to let you see what I am trying to explain, I have this example because when you say a statement, you have to understand we are reasoning, we are thinking about several things at the same time. Our brain is very complex. And for instance, when you say this sentence, the boy saw the dog in the square, the person could be in the square or not. And the person is using the same statement. When you are in the statement in the square, probably you are reasoning, okay, it's very evident that I am in the square and the dog also. Or you are with a friend and you are speaking to a friend, and you and the friend are not in the square, and it is very evident that you are not in the square. But any case, this ambiguation is pragmatics. It's not even semantics, it's pragmatics. At the same time, the deep reasoning, the reason you are speaking that way depends on the context also, and probably you want to mean something very, very different at every case. So reasoning is deeply related with the pragmatics, and to perform automatically this understanding of how the reasoning and what is the deeper understanding of this type of sentences is very, very difficult, because you need to be inside the brain of the person that is performing the communication. But as you may find out right now, you cannot explore all these alternatives. So, okay, you have a communication and you have a problem that is up to date, out of the scope. But you can process something, you can use a reduced universe, and you can think, okay, I will gather part of the communication, part of this reasoning of the producer, of the sender of the communication. And one of the most traditional approaches to do that is the context-free grammar, TFG. But you must, to understand, this is a kind of simplification. This is an outline of the communication. even Noam Chomsky, one of the fathers of these types of approaches, he also stated in his books that you can understand deeply the communication. You can't perform full semantics with these types of approaches. So if you are trying to perform a sentiment analysis or something like that, you have to take this into account because you will need some extra information to perform a proper processing. So let's go with the context-free grammar. Context-free grammar, something very classical in the field, has four main elements that are a set of non-terminal symbols, commonly known as variables, a set of terminal symbols, a set of rules that we will use these rules to produce new sentences and to find out how the non-terminal symbols relate to each other and how non-terminal symbols relate with the terminal symbols. So prediction rules has this name because it is intended to be something automatical. But up to date, we have a kind of probabilistic engines that can produce sentences in an automatical way. But as you know, they are not semantically correct, not always. We can produce automatically certain types of sentences, but the main use of these context-free grammars is nowadays just to understand and to translate to other languages. And this is just the automatic production of language. This is part of my current researching, how we can gather semantics and pragmatics in a simple way. So at the end of this seminar, I will speak some very shortly about my current work. But by now, we will keep this context-free grammar and how it is currently used. Take into account that this context-free grammar is from 60s, so it is not something new, but it's very used. So it is important to you, if you don't have heard about it, just to pay attention and try to find out how it works. You have a start symbol, and this symbol has no other function but to say, okay, we'll start producing a new sentence from this point. And now, let's see how it works. This is Noam Chomsky's tree grammar or joint grammar. You will find this type of graph with several names. It is not relevant what name you use, but you have every element here. You have the starting symbol that has not other, it's a position symbol. You can see it's a dummy symbol. Just to the node, you have a sentence that collapses to this node. And this is a tree, and every sentence in this universe is a tree. Every sentence could be a tree. There's not a unique way to build these trees. And as I have just told you, many times you use these graphs just to understand an already produced sentence, you don't use it to generate sentences because it is very, very hard to do that. But we use something very similar to produce, for instance, in a chatbot, you use something similar, but this is not this content-free grammar. Okay, so the generation is supposed to be from top to down to the leaves. The root node is the starting node. These are non-terminal tokens or symbols that denote, for instance, a noun phrase or a pronoun, verbs, something like that. And these are what we call, in linguistics, we call it syntactic labels or syntactic tags. You know, every word in your language could be an action, that is a verb, or an object, concrete or abstract, that is a noun, or we have several or diverse types of words. Every type of word is denoted as a linguistic category. So on the bottom level of the words itself, you have these syntactic linguistics labels. But upwards, you have other types of labels that are related or correspond to aggregations of words. For instance, if you have an article and a noun in your grammar, you could form a noun phrase. And if you have a verb with a noun phrase, you can have a verbal phrase. So the relevant thing here is that you can choose which tokens, which non-terminal tokens you will use for your context-free grammar. This is not something statical. You can dynamically determine which tokens and what number of tokens. It depends on what you want to process and what your system wants to have to perform. So in this case, you have certain grammar with certain linguistic tags or tokens or labels that you have already chosen, but because you have a goal and a scope predetermined, and you have a lexicon. The lexicon is, I can say, it's the more dynamic part of this context-free grammar, because every time you have a new word, you have a new lexicon. For instance, if you have a verb, eat, a word is eat, but you have eaten, eating, you have suffixes, you have prefixes, even for the words. You have complex words, you have composed words, and so on. So every time you have something changes, you have a new entry on your lexicon. So there are some shortcuts in the field that we have, for instance, stemming. These are shortcuts for these types of problems. But any case, if you don't want to consider it, you can add or append new words, and it's not a problem. But you have to cover with your lexicon every word, every possible word of your communications. So I have here a short example is I eat the salad with chopsticks. I is the pronoun, and my context-free grammar has determined that yes, I can process a pronoun. So I is a pronoun, and I have chosen to use three letters, PRO, to determine that something is a pronoun. This is very important. What is your arrangement of words and tokens, because you have to follow your lexicon in order to succeed. Every time you have a pronoun, you have to use these three letters, PRO, and now no pronoun, no pronoun, or nothing else. This is very important because afterwards you can perform statistics, and from the statistics you will perform some inference with heuristics. So heuristics, the most successful heuristics, some of them are IBM zeros, IBM 1, or some others are probabilistics. They can use naive Bayes or other approaches or other heuristics. Most of them are based on statistics. So if you want to succeed with your grammar, you have to decide very, very precisely which tokens you will use in your context-free grammar. After you have detected from the lexicon which categories you have, then you have to relate them to get the tree build up to the starting symbol. So pay attention, because you have to note that the building, in fact, when you are using this context-free grammar, is bottom up, not top down, even though it is aimed to produce from starting node to leaves. But after you have this level, you have to group them into more deeper levels, and you have to collapse them into other nodes. So you have from left to right, if you read from left to right, or you have to proceed from right to left if your language reads from right to left. But most of the cases is from left to right. For instance, in English or Spanish, you need to start from left to right and try certain rules. And the first rule that you can try is you have to apply the rule. Most of the time, the rules are ordered in a proper way for certain contexts, but they are not properly arranged for other contexts. And this is part of the pragmatics problem. And we cannot cover these types of problems with these context-free grammars, and we have to go on as if always we have the same arrangement of rules. And this is very important to note, because afterward you will validate this processing with some statistical percentages or something like that, and we have degree of precision very low. For instance, for this type of context-free grammar, if you have in a real world a 70 or 80% of precision, is very, very good. It is more likely that you will have between 50 to 70% in a real world. I'm not speaking about my colleagues that sometimes have very tremendous percentage of precision, but they are not realistic. They work just for certain corpus, I mean, a certain set of sentences. But you have to be honest, and I'm honest. I have to tell you that we have a 60-70% of precision in real world. So this is something that relates. This is another example just to show you that how it works in an ambiguity in an ambiguous statement. For instance, if I have this statement, I see her with glasses. For a context-free grammar, it's very, very easy to understand which are the meanings that I could have, because if you can see, these trees are different, the way they collapse up to the start symbol. I can see which meaning is the current just using one or the other parser tree. But again, you can build up these trees the way you want. It's up to you which one you are using, except for the situation where you have, when you have enough information and it's not common, it's not frequent that you have enough information to know which one you should build. So it is more probably that you will build the one on the left, because rules apply from left to right, and the first rule will detect this combination and will go this way. Except you change the sequence of your rules and you will get always these types of rules. So as I have just mentioned you have some databases, or you can compile textual data in something called parser tree banks. These parser tree banks are texts that are collected and processed by someone previously, and they have performed this labeling, these rules, and this decision of which tokens to use. So these parser tree banks are always related with a set of indication on which rules and which tags you will have to use. So you are not free to determine here how you will work with sentences and words. Another thing is that the parser tree must to be in certain language. So you will find different parser tree banks languages, each with different precisions, with different set of tokens. And most of them are not big enough. Just to make you an idea, for performing a standard training of an inference tool, a standard heuristic needs to be trained with about 50,000 parsed sentences. But a corpus, we name a corpus a database with of this type. A corpus is always about 1,000 words or a dozen of 1,000 words. And if you make some easy calculation, you will have, if you need a certain training, you will need at least 100,000 words, not 1,000 words. I mean, corpus are very reduced, just for practical using. A standard test could take about 3,000 parsed sentences. Again, if you have an average of 10 words by sentence, you will need about 30,000 words. So you can make an idea that the size of the parser tree banks needs to be very, very big. So we need very powerful machines and much processing. Usually the information, the parser tree, even any other corpus, are transcribed conversation, books, newspapers, magazines, even posts in a social media, etc., etc. You can gather any information is useful here. This is an example of how looks the parser tree bank. You have here a graph transcript something that looks like a Lisp language. And you have the tokens here. These are the starting level, the branches at the next level, and the leaves are in the inner level. Here you have some tokens, very, very fine-grained, like noun phrase here that are pre-Vinken. You may choose to have Pierre and Vinken as a wall noun phrase, but here this parse tree has split even a single noun every word by word, but some parse tree are more simple than this. And you have several levels. You can choose which level and which the degree of granularity you may choose. So let's explore some cases. Here you can use this free tool, this on the web. I will start it. This is a syntax tree generator. It's for free. You don't have to pay anything. It's very easy to use. For instance, you can change it on the fly. For instance, I changed some end token and symbol. I can add more branches here. Sorry, I have to on something. I can use something like this, like an adverb. And then you can see on the button is changing in the same way. And this is a WAG is something like I was just telling you that you can aggregate more than one word in a single label, but always it only works in the button level. So let's go back and I will show you some examples. There you have one, the child puts the toy in the box, and you have to determine the linguistic level of every, the linguistic level of every word. And afterward, I have already determined the lexicon is an article, a preposition, nouns, child, toy, box. And if you see how it works here with the syntax tree generator, I perform this tree very easily. If you know Lisp or APL functional languages, it will be very easy for you. This is the program, so you can take it from here and try it on the internet. Pay attention on the lexicon. It's very, very reduced here because we just have one sentence, and you have a set of rules that seems to be very many, but consider that these same rules could generate thousands or hundreds of sentences. So the lexicon will increase progressively, but the rules not. So even if you can have here a reduced lexicon, you will see that in the second example, we need to add more rules and sometimes more lexicon. The second sentence is how the price of the apple has changed lately. Here we have to add some rules and to modify some rules if we want to be very efficient. Always consider that if you can have a very reduced set of rules, you will be more successful in your context-free grammar because your statistics will improve and all your work will improve. So we have these rules, we have to add these rules to produce this new sentence with this context-free grammar. And we can here perform a choosing because the option is to have the preposition changed by a rule to a modifier, an article to a modifier, or you can opt to have a set of rules for prepositions and the same set of rules for articles. That's up to you. and it depends on your needs. Here in the bottom is the new program, if you want to try it on the internet, and the lexicon, as I have just told you, you have these new words appended. And the last example is uses the same rules, but you have to add new words. So let's see some applications of these types of tools. You have to, I have to remark here that there are many other tools that are using induction trees and clustering or perform the regression and some other heuristics that I have not mentioned here because I don't have enough time, but you have a complete set of tools with machine intelligence and computation intelligence, and if you want to explore them on the web, you have many very interesting tools. One of the applications of natural language processing in general is automatic text translation. I had tell you about this previously. You can translate from or to any language. You can this way support to automatic web translation, web content translation. You can build assistants for marketing in several languages or even in your native language. You have to note here that we will not replace humans in complex contexts because we can't provide pragmatics. We can't cover complex sentences here. And you can build your own chatbots. We have AIML. You have many tools for build your own chatbots in a very easy way. And sometimes chatbots are confused and mixed with speech technologies, but chatbots doesn't need to a chatbot doesn't need to be with a spoken language. Most of the chatbots, in fact, are in textual language. So you can use, it's up to you, speech technologies, but you don't have to. You can build your help desk and assistant for any enterprise, and it's very nice to chat with an automatic device that seems to be quite intelligent. You can use natural language processing for information retrieval. In fact, this is one of the most ancient uses for natural language processing. You can build your own smart application programming interface. You can perform automatic indexations. In fact, more than 30 years ago, Teuvo Kohonen has built the self-organizing map, and it's a neural network, a very interesting heuristic for you to try. You can perform automatic summary, just like Google performs every time you perform a query on the web. You can perform sentiment analysis just to automatically know who is browsing in your website or who is performing a certain opinion statement in your Facebook or in your Instagram. You can detect automatically the mood of people on the web, and you can even draw what is the network relationship, the relationship in certain communities. So you can use it many ways for social, psychological understanding, or even politicians use this to know how is the mood of the public after certain speech or lecture. And much more. You can use this for digital medical history, curriculum classification, many paperwork that is very boring and very slow. You can speed up them with these types of tools. Um, let's see how are some of the benefits of using this type of techniques. You can simplify the communication with machine. In fact, it was one of the first using that we wanted to research on, because we're very concerned about how people will interact in the future with machines when there are a big amount of documentation, very hard to find what is in there and what not. So for document classification, translation, streamlines, with manual paperwork, and to perform, for instance, decisions on big data, you need this kind of natural language processing. So, in fact, this is very actual to find deep learning, just to find out what information is on the web or in a video or in an image. So natural language processes is in the center of the science right now because of these benefits. Now let me show you some real examples. These are all three of my projects, of my current projects. They are BioTech, TA, and DAISY. BioTech is a natural language processing application for autistic spectrum disorder. This is a disorder where people can't speak and can't understand natural language. It is a very increasing pathology, and people can't revert this status. They can improve the way they behave. It is characterized by stimulus and repetitive body behavior. They can produce sounds, they can't produce any speech, they can't use language to communicate. So what we use here are very natural language processing tools, very much mainly morphosyntactic linguistic wavelets, to translate from sounds and movements and stimulus to tokens. These tokens, like in the context-free grammars, have to be predetermined, and they explain what this stim means, what a certain sound is meaning right now. The main thing here is that it must be performed automatically, because every patient has its own language. So you can't perform this task manually because you need something that has to be customized to every individual. The second project is TA. TA is a project that performs automatically indexation and information recovery from regulations in an academic field. So you have here the main architecture. You have a set of documents that are automatically processed by natural language processing, just to get a set of patterns, which are used, a kind of vectors. We can see it as vectors. And this bag of vectors are processed by natural language processing with some clues, with a certain dictionary, with the slang, to contextualize, to insert the pragmatics field here. And then you expand the original documents with certain metadata that are used with this, with a self-organized map, in order to expand the initial query and to get some extra information about the corpus of regulation. And the chatbot will, this is the front end is a chatbot, and the back end is a natural language processor. The chatbot will answer you in your natural language. It was implemented just for Spanish up to now. it is pending for us to implement in other languages. But you can see here the Android version. We have both desktop and Android version. This is the login screen. And this is the screenshot with a query and the answer. I want information about academics, and the answer is something like, I have found the following answer. What do you like this, professor? And something like that. The third and my last project here is Daisy, that tries to find from a current dialogue. It converts a dialogue, spoken or written dialogue, transform it into a corpus, not a tagged corpus, but a corpus, and performing some processing with entropy, fractals, and natural language processing. We have with my team find out 7 rules of language thermodynamics that is very successful to produce new language and to understand how is the reasoning, the deep reasoning behind the sentences. So deeper semantics is possible to get using this type of language thermodynamics. This is the end of my time. I think I am 9. I have spent 50 minutes, so that's all for me. Thank you for your time, and I'm available to answer your question if you have some. I will stop sharing my screen.
Thank you so much, ma'am. Any queries from any of the participants? Yeah, feedback link will be shared in a minute. Pradeep sir, you raised your hand. Any queries?
You can write it on the chat box if you can't speak.
Question?
Yes, Pradeep sir.
Yes, very good evening. Very nice and informative session. One query I have to ask, based on the NLP, in the clinical text, either it can be discharge summary, or it can be admission summary, or any investigation reports. We want to create the relationships. We want to identify the relationships. From that relationships, I have to build a knowledge discovery system. May I know what approach if I use, it will be convenient.
If I understand you want to know how to perform a deep relationship between your sentences in your clinical database, your clinical corpus. Did you target your corpus?
What's that?
Do you have a tag in your corpus? Did you detect sentences, linguistic labels have, or just the data?
I am having a data set of electronic healthcare records.
Mm-hmm. So
which can be a discharge summary, which can be investigation reports, which can be admission summaries, case history. From all the 3, either I have to establish a relationship, and I have to discover a knowledge from that knowledge has to be represented to the outside world through some statistical tables or through some graphs.
Mm-hmm. Yes, the production that you may perform with this type of information. First of all, you have to understand that you are processing in a reduced. You need to reduce your universe, the thing that I was speaking at the beginning, because you need to manage a very precise slang. So the first of all is to apply tools that are usually known as reduced domain. If you apply this, you will get better results because these are more closely to be a probabilistic tool. So probabilistic tools like naive Bayes, inference trees like an ID3 or something like that are very performant. They are very good for that. So you can extract, you can summarize, and you can even perform recommendations. You can perform a graph of knowledge
Yes,
for
yes.
and to present this. You can expand your own reduced summary or slang, and you can perform something like Google have a automatic summary. And I think you may want to reduce this textual information from the physician to other administrative or other outer person. So you can perform it with statistical tools that are on Python. R language is very good, and you
Yes, sir.
can use Octave also. I personally use very much free and open tools like Weka or Python. Python is in fact a very good tool to perform in this type of processing, but I have to warn you that the corpus, for instance, the Stanford
Yes.
corpus is the best one you can use now. But if you use the Stanford corpus, you will get a 30 up to 40
Okay.
percentage of precision. So please use your own dictionary, your own trained corpus, because you will get poor results in any other case. So I can recommend you to first start with your own lexicon, and second, train your own corpus, because the standard tools are not well trained. And I can find out, I guess you are trying to use it in Hindi, not in English or in Spanish or in German or in any other language. So in Hindi, the precision is very low. So you need to train in Hindi your own lexicon.
Okay, one more doubt. One more clarification. I have seen in the slide. I have seen the slides summarization. My one simple question is there. Is there any mechanism? Is there any mechanism to extract the theme or moral of the text what we are given? Take for example, I will give a input the text a story. The NLP has to process it, whatever the techniques, pre-processing techniques, it has to process it, and it has to fetch the theme of the story or the moral of the story. Is there any possibility, madam? Can you please highlight any few
Yes,
tips for
yes,
that?
yes, definitely. You can use neural networks for that.
Not summarization. I want moral of the story.
Yes. You can find it out from data. This is a data-driven training, and you can use neural networks for that, but not any neural network. You have to try certain architectures, for instance, convolutional or regressional neural networks, just to be good for that type of information. But yes, you can do that.
Okay. Thanks a lot.
You're welcome.
So I think, ma'am, there is one more question which I would like to read from the chat box. This is the question from Dr. B. Shivkumar. He has asked to highlight on email filtering and automatic summarization using NLP.
Yes, there are many tools for filtering. These are many current firewalls in the internet, or even the private tools, paid tools. You have filtering, and they mostly use neural networks. But I have to warn you again that neural networks has many. It's a very strong tool, but it has many problems, because you can use it at any time, in anywhere, but you have to use it properly. It is very sensible for the way you train the neural network. So you can filter it using support vector machines and training the support vector machines with a neural network. A simple multi-layer perceptron can work that. You can do that. Or even if you want something more complex, you can use it. But a simple multi-layer perceptron with 3 layers, you can use it. But the problem here is that the sequence of the data is very, very important. And the way you need to choose an activation function that is sigmoid or something like that. And you have to tune up the parameters very, very well. Because some people use neural networks to perform this task, but they, at the end, they filter too many mails that are not dangerous or threat. So you have to tune up very, very well the neural network, but you can use a support vector machine and a multi-layer perceptron to do that.
Thank you so much, ma'am.
You're welcome.
So I don't think we have any question. So Dr. Daniela, madam, I extend my heartfelt gratitude to our respected speaker, Dr. Daniela, to take out her time in spite of her busy schedule to grace this event. Actually, madam was busy completely this month. She was ready to deliver the talk last month, but due to some LIC committee and all that, we could not arrange for it. Thank you so much, madam, and for your excellent presentation and making this webinar interesting. On behalf of Dr. AIT, I express my sincere gratitude to all esteemed delegates of the webinar for their presence to make this webinar a grand success. I would like to express my deepest gratitude to our management, Panchajanya Vidyapita Welfare Trust, for all their support and guidance. I thank our principal, deans, HODs, and coordinators of this webinar, mainly Anand, and one more coordinator, Mrs. Ashwini, for all the support. We really appreciate the time you have all taken, you have spent, even after your office hours. Thank you, one and all. Thank you so much.
It was my pleasure. Thank you, all of you.
Thank you.
Bye-bye.
Bye, ma'am. Thank you.
ಹಲೋ
Anand,
ಹಾಂ ಮ್ಯಾಮ್ ಹೇಳಿ ಮ್ಯಾಮ್.
ಆಯ್ತು ಫೈನ್, ಆಯ್ತು. ಥ್ಯಾಂಕ್ ಯು ಸೋ ಮಚ್.
ಹಾಂ ಚೆನ್ನಾಗಾಯ್ತು ಮ್ಯಾಮ್.
ನೀವಿಲ್ಲ ಅಂದ್ರೆ ನನಗೆ ತುಂಬ ಕಷ್ಟ ಆಗ್ತಾ ಇತ್ತು.
ಹಾಗೇನಿಲ್ಲ ಮ್ಯಾಮ್.
ಫುಲ್ ಬ್ಯಾಕೆಂಡ್ ನೀವೇ ನೋಡ್ಕೊಂಡಿದ್ದೆ. ಇಲ್ಲ ನಾನು ಯಾರು PhD ಸ್ಟೂಡೆಂಟ್ಸ್ ಇದ್ದು ಮಿಕ್ಕಿದೆಲ್ಲ ಮಾಡ್ಬೇಕಾಯ್ತು.
ಇಲ್ಲ ಮ್ಯಾಮ್ ಆಗ್ತಿದೆ.
ಆಯ್ತು.
ಹಾಂ ಚೆನ್ನಾಗಾಯ್ತು ಮ್ಯಾಮ್.
ಚೆನ್ನಾಗಾಯ್ತಾ?
ಹಾಂ ಚೆನ್ನಾಗಿ ಮಾಡೋದು ಅವರು ತುಂಬ ಸಾಫ್ಟಾಗಿ ಸ್ಟಾರ್ಟಿಂಗ್ ಫಸ್ಟ್ ಟೈಮ್ ಕೇಳೋದು ಅನಿಸ್ತು.
Welcome.